I emailed Bob there, but I didn't hear back from him.
What is it about? This is the astronomy.
Do you know if he uses SIU email?
He used an SIU email? You didn't get it the same?
Oh no, I did. I sent him one, but I haven't heard back.
Yeah, he's in SIU and he's usually busy because he takes care of these things. And typically he does get back.
Okay.
So give him a few days maybe.
Okay.
If he doesn't get back, don't hesitate to just follow email.
Okay.
It's just typically there are so many things that he's a person who, if you don't get back even in a week, then that means it has gone below his inbox. So you have to follow.
Okay.
Like for example, this wire that I requested from Walker, and after 4 days he replied back to me that it is possible. And then I sent it back to him, and then it seems like beyond 25 feet, not 25, beyond 5 meters, apparently you have to put a booster. So it's more complicated than just extending the wire. So my point is that yeah, he does get back to you, but it takes his time.
Okay.
And not because he's just involved in anything. He's the one who was the main person in charge in the eclipse of 2017. So it's pretty qualified and in general, engineer resourceful. Good to know like from Murphy's Law. So
Yeah.
But that doesn't mean
Right.
everybody here needs to. And it's a veteran.
Yeah,
That's a lot of common. It's good to know. He's typically, do you know the physics computer room?
On the fourth floor?
Yeah, on the fourth floor. And there's an entrance to that, right opposite to that, there's another room. Very similar, like slightly towards the east side, around the same side. That's his, say it's his room, but it's basically a workshop and the source code. Have you interacted with Bob?
Yeah.
Yeah. One way. Oh, there are, you can see it. Configuring. It's in someone, but yeah, Travis usually. frustrated. Okay, so yeah, homework 3 is due on Friday. Oh yeah, I need to wear a mic, right? I forget that.
Okay, hopefully better.
Yeah, sounds good.
Yeah, okay. Okay. We want to today get the main equation that's necessary for calculating the magnetic field due to wires, like current carrying wires. And some of it you have already seen in introductory level physics courses, and partially you haven't, in the sense you haven't seen the magnetic vector potential. So you should be able to connect half of it at least in a very intuitive way. But we will have a slightly more mathematical expression here because we want to do it in terms of Green's function. But I won't specifically use the function itself, but it will be very clear, very similar to what we did in electrostatics. So that actually tells me that, okay, let's very quickly review electrostatics. Main ingredients in there. Recall that is divergence of the electric field was equal to, there was this, because we are in SI units, there is this permittivity of vacuum that shows up, and there is a charge density. So it's in principle a function of R, right? And this is also a function of R. But let me not write that to avoid some clutter. And that is del cross E is equal to 0. Right? In magnetostatics, it's exactly opposite. Divergence is equal to 0, and curl is given in terms of the current. But once the curl is 0, we say that since curl of a curl is equal to 0, that seems to suggest that electric field can be written in terms of another function, which is gradient of something. Right? So the electric field can be written as a gradient because the curl of the electric field is 0. In the magnetic field, it's opposite. Divergence is 0, so the magnetic field is a curl of a vector field. Like that's a magnetic vector potential. Substitute this in here. So once you know this, we are going to solve for the electric potential. Put that together because its electric field is a gradient. Gradient dotted with a gradient is del square, right? So recall del square is del dotted with two gradient operators dotted with each other. That's your gradient square. Exactly like a vector, this is a scalar operator in a sense. It's the second derivative with x square, second derivative with y square, and second derivative with z is the Laplacian. So this is the Laplacian, if you want. So if we were to put this inside here, we get an equation for the electric potential in terms of the Laplacian, right? Laplacian square, Laplacian or negative of the Laplacian of the electric potential is equal to 1 over epsilon naught times the charge density. And again, our goal is, given the charge density, what's the electric potential? If I know the electric potential, I can calculate the electric field because derivatives are usually easy, right? That's the idea. And if you recall, our expression for the electric potential was the negative Laplacian is equal to, this comes out to be 1 over 4 pi epsilon naught times an integral of charge density over r minus r prime. How do you want to interpret this? Notice for a point charge, the main idea here is that if you have a single point charge, if you have a single point charge, its electric potential is q over 4 pi epsilon naught. So let's say this is 4 pi epsilon naught, and then there is a q over r minus r prime. What is r prime here? That's the position of the charge, right? R prime here is the position of the charge. So what are we doing here? If there is a whole charge distribution, you sum over all the charges, and each charge contributes you this much, right? So this is called the superposition principle, if you want. So if you know the charge density, simply do the integral and you get your electric potential. Once you have the electric potential, you can take the derivative of that and you get the electric field. Is that very clear? Any questions on that? Again, notice this is in principle for a point. You can say the electric potential due to a point charge, but this is also for all purposes. This is negative of del square, right? If you were to get rid of this q and epsilon naught, that's just minus del square, right? That's if you have an operator acting on something to give you something else. If you were to invert this, you will need this structure. That's called the Green's function, and we went over it to a certain extent last semester. And later on, if you do electrodynamics more in detail, there is a formal way to get that. The main idea is, again, this operator has always a solution of this kind. But otherwise, if you don't like that, if you want to be intuitive, you say that for a point charge, this is the electric potential, and this is a superposition principle, right? You add up all the point charges, and you get that. Okay. We want to do this for magnetostatics now, which is, as I said, very similar. So let's see how this works for magnetostatics. So, let me go to the other board. Okay, so let's do. Magnetostatics deals with a situation where the divergence of a field is equal to 0 and the curl of the magnetic field is equal to mu naught times the current density now, which is a vector. This immediately implies that the magnetic field has to be or can be written as a curl of a vector potential. You can write one unknown in terms of another unknown. So if you get the vector potential, you're good enough, and you can put it back in there. Use the same trick as earlier. We will try to find the vector potential and then later get the magnetic field using that. So we will substitute this into your other equation. So we get a new equation in terms of the curl of a curl of the vector potential is equal to mu naught times J. And also remember that this vector potential has an arbitrariness in this, right? So there is a gauge involved. So there's a gauge dependence or independence, if you want. Gauge independence. I can go all the way till here. And the gauge independence was that if you redefine your vector potential in terms of an arbitrary scalar potentials, any lambda, that is r, in principle it can also be r comma t. So this can be, like, even though we are in statics, this is much more general. This construction, notice, this doesn't require statics, right? Because the divergence of B is 0 even beyond statics. So this immediately implies this. And this independence is there even in all of electrodynamics. So that's why I introduced that T here. But at this point, we have actually killed the T dependence. We would like to solve for this equation. And remember earlier we had the Laplacian or the gradient square that was coming in, then we immediately know the answer that this is given in terms of 1 over r potential. But that's not a gradient square. This is a curl of a curve. But can we simplify this? Let's expand this out. Remember your vector operation. So first one comes from here, and notice del commutes with itself, right? You can move derivatives around itself. So what we get is the gradient of the divergence of A, this is using the vector identity, minus of, this is the independent vector in the second term, and this is squared. Is equal to mu naught as J. Okay. You notice this gradient square that's showing up, that's exactly the Laplacian, right? So if it was only this much, we're good, right? We know how to proceed, but it seems like there is this additional term which really spoils everything. But that's where the gauge dependence comes in. You have a choice to a certain extent. Remember, in electric potential, you set phi equal to 0, right? Somewhere you can set phi equal to 0, and this is a vector field you're talking about. So there is more independence now. Since it's a vector, you can either set 3 components of a vector to be 0, or there is a whole feature as far as you're not disturbing your magnetic field, you can add in anything you want. Like we had a divergence of lambda here, or sorry, a gradient of a complete vector. So we have to be careful in here, but it turns out that you can choose. So from now onwards, you will choose a field which is, this is equal to divergence of this is equal to 0. We're going to choose that. Okay, so always we have to make sure that we check this. So this is a gauge choice. So this is called the Lorentz gauge. This is Lorentz. I think this is Lorentz. Not, there is no T in there. There are 2 independent people. The guy with T, the Lorentz force is was a significantly a more authoritative person in those times. Lorentz is different, guys. So this is Lorentz gauge. And most of the time, almost the whole semester will stick to this, or I should say half of the semester will stick to this choice. So this is equivalent to, even though I'm not telling this anything more than this, it is equivalent to choosing the phi equal to 0 as a ground. In principle, you can set it anything else also, right? So, but how can you check that, even though I'm just stating it, every result that you get, you have to check that whatever A you get, it actually verifies this. If it doesn't verify, that is a problem. But most of the time, the way we will do it, it will be automatically set in like that. But sometimes we should be careful. So there will be some examples where we will check that this is equal to 0. But in principle, every example should be taken as an exercise for yourself. So Lorentz gauge is going to be del dotted with A is equal to 0. So that becomes an additional requirement if you want. Okay. If you set that to 0, as a simplicity then, right? So this is set to 0, that's a choice now. Now that's within the choice, our vector potential satisfies this neat little equation, which is exactly like the electric potential, except that this is a vector now. Right? The source is a vector, field is a vector. Otherwise, this operation is exactly the same. So I can use all of the electrostatic solution there and immediately write a solution for vector potential, and that will be equal to vector potential at point R, observation point R, will be equal to, remember that instead of epsilon naught in the denominator, there is a mu naught in the numerator. So instead of 4 pi epsilon naught, we have mu naught over 4 pi. That's because mu naught is in the numerator. And the same integral, this is a superposition principle. This time we are superposing the current densities. So contribution from each current density adds up. Divided by R minus R prime. Notice this is very similar to what we have in charge densities. Add up all the point charges, but here we are saying add up all contribution from current densities. The way you want to look at this is that if you have a J here, that's a particular region of J. Each element here contributes. Right? Each element here contributes this much. So if you want, this is equal to d cube R prime times J. Right? That's a source if you want, the volume multiplied by J, which is also equivalent to, this is also equivalent to I times dl. The dl is the direction in which the path is going through. Right? Typically, when in introductory level physics, we, since you don't want to have 3 integrals, you motivate it in this terms. And otherwise, it's exactly the same, except there you're not talking about vector potential. There you directly go to the magnetic field. Here we are going to the vector potential. And then from this point, we will go to the magnetic field. Okay. So that's going to be our basic first step in here, right? The moment you have Maxwell's equation, use the Lorentz gauge, and you immediately get the vector potential. And if I have the vector potential, I can calculate the magnetic field for this just by taking the curl, right? Where is my magnetic field will be, let's say here, B will be del cross A, which we will do just now. But before that, maybe let's do an example. Or should I? What's it? Yeah, so let me actually evaluate the magnetic field also, and then I'll come back and do a very simple scenario whether we can calculate the vector potential or not. Okay. Okay. Any questions at this stage or comments? Anything? Right. One, two, three, four, five. Yeah, Wahid also in the class, right? So we have 7 of us now. Is it? Oh, I thought we were 6. My, okay. Change. Okay. So for any given current density, we have the vector potential to be given by this. That's what I've motivated. Let's say A or so let's immediately calculate the magnetic field, right? Magnetic field at the observation point R is del cross of A of R, right? Notice in these expressions, sometimes it becomes important to, since there are 2 variables, right? Position R and position R prime. One is the source and one is the observation point. This gradient is with respect to the observation point. There could be a gradient with respect to the R prime also. Right? Later on, we will see sometimes we will come across those situations. But for now, it is just the gradient is acting on this R. Does it act on this R prime? No, right? Because it's with respect to R. So there's only one place this hits, and that's this. It can enter the integral because this is a derivative in R. This can enter that integral. And the only place where it will hit is this R. So often the confusion is why does it hit on R prime? And often you tend to do that, but that's not correct. It's only this R that it hits, and it can easily reach that because the integral doesn't depend on that. So using that, I say mu naught over 4 pi. This is a curl of a vector when A has a vector nature in J. So after I enter the integral, this is a scalar. The denominator is a scalar whose curl you take, or it's not the curl, it's a gradient now, right? So this is R minus R prime. That is, it hits only on this. This gradient operator hits on this, and whatever comes out has to be crossed with J. Is that clear? Like I'm doing it at a very generic level. Later we will do this more explicitly, but the point here is that this gradient is acting only on that R, so which is a scalar piece there. So the gradient acting on this scalar, and then it gets crossed with the J of R prime. That has the form of gradient of 1 over R. What is gradient of 1 over R? Very good. Very good, right? So this is like the electric potential due to a point charge. So this is negative R hat over R square, right? So this should be thought of as an electric field due to a point charge. This is the electric potential due to a point charge. And if I were to put a negative sign in between, that's the electric field. since there is no negative sign, so the way to think of it is this, right? This is the electric potential 1 over r. Negative gradient of that is the electric field. So this is an identity if you want. If you move this, this is at the origin, right? R is being measured from the origin. If you were to move this a little bit, and I can go until here. So if I were to instead make this more general, r minus r prime. That just means that I moved the origin to r prime. Right? That's all I have done. So the whole thing will work out again. Just note that this is the same as vector r over r cube. Right? That's also can be written in that form. So this will be equal to vector r, which is now r minus r prime, not a magnitude, this is parenthesis, divided by the magnitude cube, magnitude of that vector cube. That's what we did in electrostatics a lot. So that's an operation which is pretty much saying that the electric potential due to a point charge is the electric field. It shouldn't be a surprise at all. Any questions on that? Okay, if we use that, we put that in here, right? But there's a negative sign on this because this is with a negative operator, so I had to put it on the other side. So I get this is negative of mu naught over 4 pi times d cube r prime times r minus r prime parenthesis cube crossed with there's a negative sign in the front. I can flip the cross product, right? This is a vector crossed with another vector. A cross B is equal to minus B cross A. So use that to flip this. And we get the expression for magnetic field, which is what we will use from now onwards, is equal to the current density crossed with the field expression for a point charge, but in this case, this is due to the contribution from the line, right? So the analogy is that this is the same Laplacian operator, inverse of the Laplacian operator. Okay, and that should be a familiar expression. Where have you seen this before? In your introductory level physics, there's a name associated with this equation. When you calculate the magnetic field, yeah, exactly, right? So this is Biot-Savart law, right? That's what you've seen this, and typically you don't see it in this form. Again, let me rewrite this a little bit. There we don't talk in terms of current density, it's usually in current itself. If you were to, so this is typically written as dl. So this whole thing is nothing but IDL. So dl, right? So where the integration is happening over all the currents, right? Crossed with r minus r prime. So that is an inbuilt realization that, okay, each contribution from the current wire actually contributes this much, and you add up this whole contribution. Okay. So that's the expression we will use for magnetic field. This is the expression for the vector potential that we did. while we are here, yeah, 15 more minutes, let me do one more step before I do any example. And that is that because there is this mysterious Lorentz gauge that I used and I did not emphasize too much. Basically, it is a deeper concept. There is a lot more subtleties that comes in. But at least I can do one thing. I can check that this expression that we wrote for A satisfies that at a very generic level. Like if that satisfies, at least that's a slightly more more satisfying than just blindly using that. So let's actually start from the vector potential formula and see if it actually satisfies the Lorentz gauge. Okay, so okay, so we have A vector potential, and all this is happening very generically, but we will do examples, very simple examples like a straight wire, circular wire, and so on. D cube R prime and right. We want to show that the divergence of this is equal to 0. So when we take the divergence, notice the vector dot product happens with J, but that's a function of R prime. So this doesn't really operate on that R. It only operates on the free R, right? Not the primed quantity. So this is the same as 4 pi d cube R prime. The vector operation or the gradient operation goes through J. So it goes through J, but its vector combination has to be dotted. So these two are dotted. Correct? But it can go through the J because it's all R prime. And it hits this R minus R prime. And we already know how this operates on that, but we don't want to go along that path, because if we calculate that, then it becomes, we know that it is in the structure of the magnetic field, correct? So what we do is, this is a function of R minus R prime. We want to use that feature. So let's say if you have d by dx of exponential of x minus y as a general function like that, and what is that equal to? That's simply e raised to x minus y. That should be straightforward. But what is d by dy, or let me say x minus x prime? What is derivative with respect to prime of e raised to x minus x prime? What is that equal to? Negative of this, right? So this is negative of x minus x prime. In general, you can notice that if I have any function f of x minus x prime, this will always be negative derivative of the same function. Because whatever be the function, you will use all your derivative operations to calculate the derivative of the function. Eventually, when you reach the argument, with respect to x, you hit this x, and with respect to x prime, you hit the other x prime. So at the end, you will always be off by a negative sign, and that is all you will be off with, which means to say that the gradient of a function f of r minus r prime will be equal to negative gradient, this time of the primed quantity of f, the same function. It will be negative of that. So now I'm going to switch from the gradient operating on this r to the gradient operating on that r, which is possible, just that I get a negative sign there. So that's equal to minus mu naught over 4 pi q prime and j of r prime dotted with, this is now primed quantity. And why the primed quantity? Why did I prefer the primed quantity over r minus r prime? It seems like it will be the same operation anyway. But no, there's an advantage here. And the advantage is that we know that what is divergence of J? What is that equal to? That's 0 in magnetostatics, correct? So somehow we should be able to use that, but we are not yet ready to use that because this gradient is not acting on that. Right? It's acting on the 1 over r potential. But if I can act it on that, then I know that that's equal to 0. And that's very generic statement for magnetostatics. And we are looking for a very generic statement that Lord's gauge will always work. So we want to do that at a very general level. So we integrate by parts. Whenever I have a derivative inside an integral acting on something else, I can actually put it on the other side by using integration by parts, correct? So let's do integration by parts. And the way you would do that is first make the operation on this side. So that's when I do that derivative acting on this side, I lose a sign, correct? Remember your, how do you do this? dx, df, here it is. Yeah, so let's say f and derivative of g with respect to x is the same as negative integral of dx derivative of f times g, and then you evaluate this whole thing. Let's say this is being evaluated at a to b. You evaluate f times g at the boundary, correct? That's what you will do, integration by parts. There are other ways of seeing this. This is the boundary. That means if it is a three-dimensional integral, then it is on a surface, right? So here, this will be equal to plus mu naught over 4 pi d cube r prime times divergence of j and you have 1 over r minus r prime. It doesn't matter what it is because this is equal to 0, right? In magnetostatics, that's equal to. There is one more term now. That is this evaluated at the boundary, right? At A and B. The boundary of this is a surface, right? So this has to be taken all the way on the surface. So that's minus mu naught over 4 pi. Right. So this is a surface, which is, if I'm doing this on all space, this is on the surface at infinity, right? R tends to infinity. So evaluate this on the surface, and this time you forget the del prime, right? There is no derivative. Oh, no. So this is a dA dot. So dA, so at the very end or whichever surface we try to do this on, but typically you want to go all the way to infinity, and dotted with j of r prime, and then there is 1 over r minus r prime. And so this term is equal to 0 because we are working with magnetostatics. That's clear. The second one, we had to impose. Right? So we are going to talk about situations where j is equal to 0 at r equal to infinity. So if, so maybe you have to require this, right? If j is equal to 0 at r prime or r tends to infinity, then we have the Lorentz gauge true to be satisfied. Right. But notice that additional condition comes in there. Otherwise, this need not be 0, right? That could be, you can imagine a situation where that might contribute. So one has to be careful about that point that you don't want to talk about current densities at infinity. And we will deal with this, that we will be taking it to infinity, but then always we had to, like I think this discussion came up last time. So we have to be careful with those. Like here also we are saying the same thing. Sometimes it is cyclic, but for consistency we have to put everything 0 whenever we can. But the challenge is that when you talk about a infinitely long current carrying wire, invariably it is going all the way to infinity. So there you have put in a condition. Here again, we are using the same condition. So it is cyclic, I agree, but we have to be careful there. Okay, and very quickly, yeah, any comments or questions? 3 minutes. And I can do a simple example maybe in 3 minutes. No, well, let's come back and do the, I'll basically do it for an infinitely long wire. We'll explicitly actually put in numbers there. And it is clear that, oh, this is all goes to infinity maybe, and we will see where that happens. And hopefully that is more convincing. Okay. Yes.
Doesn't this seem a little bit contradictory though? If
Oh.
there's no source of current anywhere, if j is 0 at infinity, then there, I mean, you're saying that the current density has to start somewhere, which is opposite of what, like the.
It has to be in a loop, right? That current has to be, if you want to work in statics, you have to end, like you have to work in loops, right? Yeah. So that's why we always typically see circular wire, even a solenoid. That's a challenge with the solenoid. Somewhere it goes, but then you have to put it together somewhere. The battery connects that, right? But even the moment you talk about that, that's complicated, too complicated. So you say that, okay, let me take this to infinity. So that's a tweak you make for the mathematical simplicity, but you're dealing with these problems there. So mathematical simplicity versus this assumptions that we have made. That's and this is there in electrostatics also, but it is not so hidden in a sense. It is not so counterintuitive. Here it is slightly, we are afraid that, oh, maybe we are doing something wrong, right? As you're worried about it. So yeah, but at least this answer is probably better. Yeah. So we will do something like we'll do this completely long wire. Often, if it helps, the way you can imagine is that, okay, so J, yeah, this might be more satisfying. So this is J, so our J should be I times, there is a Z hat if you want, like direction. There will be a current I, and there will be a delta function, right, X and Y. That's your current. And you would say, oh, that's not good because it goes all the way to infinity. If it satisfies, put in an exponential in here minus of this, if this is Z direction, so let's say magnitude of Z times a positive constant C, let's say. So as Z increases, eventually dies off, like tapers off. And that's mathematically much more easy to deal with than dealing with the whole loop. So work with this. This will be at a price because now this will have a non-trivial solution there. But at the end, put the C equal to 0, and it should work out correctly. So there are ways to deal with that, and it can be done, but we won't be able to do that in that class here. Like already this one itself will be a little, you'll see that it's a little challenging. We'll have to extract it from the infinity, but we'll see that. Yeah. So, okay, helps. Okay, I'll stop here and thank you.
Yeah.
Mhm.
Any way to,
Yeah.
I guess,
People from your introductory physics, like gauge of the